So today we're going to be introducing the focus and the directrix. Now just a disclaimer, the band has chosen to decide to practice at this time, so we're going to have some musical background to our normal lesson. Don't get too distracted, but just letting you know what's going up if you hear some music going on. Now the focus and the directrix, this is part of a section called conics. And the idea is that when we look at parabolas and when we look at things like circles, ellipses, and hyperbolas going forward, they all have something in common. Now this is going to be best shown before we actually begin and start graphing it as a brief aside. So with conics, it's based off the idea that if I take two right-hand cones, I can create any of the conic shapes. If I take these cones and I cut them directly in half, I'm going to end up creating a cut that when I look at it is a perfect circle. If I take that same cut and I cut it at a little bit of an angle, let's cut it down just a little bit, not too much, I'm going to end up creating an elongated circle, and an elongated circle is called an ellipse. So my two cuts where I'm going straight across are a circle and an ellipse. And then one of the other things, if I continue to increase that angle, let's increase that angle just a little bit further. If I cut it like this, what I end up creating, that's the back end, that's the front end, is end up creating a parabola. And if I cut it very, very, very extreme, if I cut it from the top and from the bottom, end up creating what we call a hyperbola. And the neat thing is that elemental forces like gravity, they work in all of these shapes. So there's a lot of theory when you start getting into the higher maths that when you start hearing about the shape of space and the curvature of space, there's the idea that space-time is conically shaped because gravity always seems to be operating either in a circle, an ellipse, parabolas, or hyperbolas. And this idea is what we're exploring today. We're going to be cutting a cone at such an angle to where we're going to be finding points around a focus. And now the focus of a quadratic is the central point where all points are bent. The directrix is the line beneath or above the quadratic that is equidistant from the parabola as the focus. So what's going on is the fact that if we give you 3 points, if I give you a vertex, this vertex is going to be curved with a parabola. And if I give you a directrix, let's draw my directrix of y equals -1, and I draw my focus of 0, 1, any point along the parabola, it's going to be the same distance from that point to the directrix as it is to the focus. And we can see with this first one, the distance between the parabola and the focus is 1, between the parabola and the directrix is 1. So those two lines are equal. And as I extend out, I'm just going to draw a really rough shape. I know that I can measure the distance at any point. If I say, hey, I want to find the distance between this point right here and the focus, it's going to be the same thing as the distance between that point and the directrix. And this is going to tell us how the parabola is bent, in essence, how close it's going to get to that center point. Again, if we look at this in terms of physics, if I have a comet coming in, the curve of the comet is telling us how close to the planet or how close to the star that comet is going to pass. If the comet is passing very close to the star, it's going to pass really close. It's going to be very bent in that area. The further away, the more gradual that curve is. So every point along this curve is going to be equidistant from the parabola to the focus, from the parabola to the directrix. And this, without even having an equation, is going to tell us just kind of how to sketch a rough graph. There we go. So I notice that these two distances are equal, and these two distances are equal, top and the bottom distances are equal. So let's take a look at one more. If I have a vertex this time, so I'm going to give myself a vertex of 0, 2. Actually, I'm going to make these by 2's just so I can squeeze them all in. So 2's and 2's. I'm going to put my vertex at 0, 2, because I'm counting by 2's. My directrix is going to be at -4. And so what I notice is that my vertex is farther away from my directrix, which means that if I'm thinking about this in terms of like a comet path, I know it's going to be farther away from the planet or farther away from the origin. In fact, it's going to be, in this case, 2, 4, 6 units away. So 2, 4, 6 units up, I'm going to place my planet. And then as I curve the path or the projected path of my comet, realizing that again, it's farther away from the planet, so the curve is going to be more gradual. It's going to be flatter than this one. I know that the distance from here is going to be just over 3, is going to be the same as the distance right here. Which, as we can tell, this isn't quite the same, which means my curve needs to be a little flatter. Unfortunately, I drew this in pen, so I'm just going to have to kind of make up for it by kind of extending that out a little bit and then curving some more. And so if I test this point farther out, 1, 2, 3, 4, 5 blocks, 1, 2, 3. Those aren't equal. So let's kind of ignore this right side. I know that this curve is too steep. I'm going to have to curve it much flatter. Yeah, so again, we're ignoring what's over here. I drew it in pen, I can't erase that. But what I can do is I'm going to draw this curve much flatter so that when I test a point, so about 3 units away, that checks out. Let's see, this is about 4 units away. That is about 4 units away. That part checks out. So again, we're going to ignore the side over here because the two distances were not equal. The curve is going to be flatter than that. And then also, if you really wanted to, I could label my focus of, let's see, 2, 4, 6, 8. 0, 8. That means my planet is located at 0, 8 if my path is going through the point of 0, 2. So with this one, I have the vertex and the focus, but I don't have the directrix. So I know where my planet is, but I don't have the line of which I know my path is going to be bent towards. So I'm going to put my vertex, which in this case is at 0, 0. And my focus this time is at 0, 1. And so I know that if my distance between the two is going to be the same between my vertex and my focus, it's going to be the same between my directrix, which is going to end up at -1. Perfect. And so that's going to give me a point of which I can figure out how the curve is at every point. And so a quick way to check this is I know that, okay, at this point I'd be 2, and at this point I would be 2 away from both of them. which means I know I'm going to be curving through right there. And if I tend to follow that curve as I best can assume, I know the fact that this is going to be a little over 3, and this is going to be a little over 3. Again, my two lengths are going to be roughly equal. That's going to tell me that we're drawing a good rough shape of a parabola. And there we go. Might be a little too steep on this end, but again, it's just a sketch. So why don't you try this time? If we've got the directrix and we got the focus, see if you can't figure out where the vertex is, and see if you can't map a path between the two as if you're projecting a course between them. Unpause the video when you're done and see how you did. Okay, so I have a directrix of y equals -2. So I have my directrix down here of y equals -2. And I have a focus of, well, this time it's 1, 0, so it's shifted off to the right. Okay, well, it's not directly centered up, but that really doesn't matter. What I need to know is that directly between these two is going to be my vertex, which in this case, 1 unit away from both is going to be at 1, -1. And so what I'm going to do is I'm going to try and find a point that's about the same units away as it is up. So I know at this point I'm looking at, let's see, yeah, again it's about a 2, 2. So I'm going to put a point right here because we know that I have about a 2 unit and about a 2 unit distance. So I'm going to curve this thing through right there. I'm going to keep curving, so if I want, let's see, if that's a little over 3, I'm going to be a little over 3. So let's put another point right there and curve through it, which again, if this is a little over 3 blocks, diagonally that's a little over 3 blocks, we've got a good sketch going, which is going to allow us to figure out what the overall shape of the graph is going to look like. Perfect. And same thing right here. No matter where on the graph it is, now this focus is at 4, -5, so I'm going to do this by 2's. I have a directrix at -1, and I have a focus at 4, so 2, 4, -2, 4, 5. Oh, here we go. So we have our first upside down parabola. Now I know my vertex, again, is going to be directly between these points. So what's directly between -1 and -5? Well, it's going to be -3. And because I know it's going to be lined up with my focus, I know that that is going to be directly for -3. And again, we're just going to try and find somewhere that's kind of equidistant between the two. So if this is 2 units and this is 2 units, let's see, if I'm about 2 units away, I'm 2 units up. So this 2, 2 seems to be a good spot for us. So I'm going to go 1, 2, and I'm going to go 1, 2, which means I have a point that's curving right here, which means if that's 1, 2, about 3 away, going to be a little over 3. So let's keep curving just like that. Which is going to be just over 1, 2, 3, and just over 1, 2, 3. And then I'm just going to mirror that. Let's see, 2 units away, 3 units away. There we go. And there's our vertex and our directrix. So today we're going to be working on the focus and the directrix by creating an equation in what we're going to call focus form. And now focus form is a slightly misleading phrase because I'm going to make this equation in y equals a x minus h squared plus k, which is vertex form. But I'm going to make it in vertex form using only the terms of the focus. So my a, my b, and my directrix, which we're going to refer to as y, is equal to d. So let's go ahead and we're going to create a proof that's going to give us a way to do this that's going to be a lot faster. Now, we can derive this process that we're about to show right here on every single problem, but again, it's a rather lengthy solution to create an equation. What I think would be a better course of action is let's work with the actual just generic focus form, create an equation for ourselves so that we can just plug in the information and solve it. So let's take a look at what exactly is a parabola in context of focus form. So I'm going to draw my parabola like this. Now this parabola isn't necessarily drawn to scale. So like when I draw my vertex, or not my vertex, my focus right here, that's not necessarily equidistant from each one of these in comparison to my directrix. So again, it's just a sketch is really what we're going for here. So this is my directrix. So this is going to be under the form of y is equal to d, d for directrix. Typically the focus is going to be in the form of a comma b. And so what we know is that every point on this parabola, let me pick a point that actually looks like it's about equidistant. I know that point on the parabola, the distance between this and the distance between this should be congruent. So I'm going to draw my tick marks and say that those should be equal at every point along this parabola. And now this point right here is going to be the generic x comma y. That allows us to move it anywhere on the parabola. If I want to move it over here, I could. If I want to move it up here, we could. So far I have a generic focus, a generic point, and a generic discriminant. So what I know is the fact that I need to be able to relate these two to each other. So if I can create a formula that makes this distance equal to this distance, I'm good. I can rearrange that into my vertex form. So let's set up an equation for what is this distance? Well, this distance, the x doesn't matter because it's a vertical line. In fact, if I wanted to, I could draw a little right angle mark. So I know there's no horizontal distance. It's simply vertical. And I know that the distance right there is going to be however much the height is. It's going to be the full length of y. So I'm going to go all the way up, but I'm going to take away the distance down here. So it's going to be y minus d. I'm going to take the full length, which is this full length right here, and I'm going to remove the part of the length that's below the directrix, which is going to leave me with just this red line. Now, there's an off chance, let's say, that that distance is going to be over the axis, or maybe it's flipped upside down to where I could get a negative distance, which would be a negative length. We don't want that. We want the distance to be positive at all times. So the way that we're going to get around that in this is we're going to do something. We're going to square it and then square root it. So that way, for example, if this was a -2 distance, -2 squared is going to be a 4. The square root is now +2. And that's just a little bit of technical algebra there that's going to make our lives a lot easier to where it's always positive. Even if we have a somehow mathematically negative distance, depending on where this is, boom, we made it positive. Second thing we're going to look at is right here. I need the distance between 2 points. I know that goes back to basic geometry. What I can do with this is I can create a right triangle and say, hey, I know the distance of this triangle is going to be a squared plus b squared is c squared. And that distance is the square root of those distances. So I know that the distance for b is going to be the differences between y and b, y1 and y2. So I'm going to say this is equal to the distance of, actually, I'm going to do that in this bracket. So I have the distance between this y and this b. So y minus b. And because it's b squared Probably should have drawn that as a capital B, so that way it's a different, and that's going to be a capital A. That way it doesn't get confused with our focus of B. So I know it's y minus b squared is going to give me b squared. For my a, I'm going to have to look at the x's. So x1 minus x2, or in this case, x minus a. I know it's a squared, so I'm going to square it. And then to get that, I'm going to square root this entire side. And now this is what I'm going to work with right here, is I have everything I need to create this equation. So let's take a look at this. First off, I'm going to need to get rid of these square roots. So my first step is to go ahead and square both sides of the equation. And what that does is that frees me up to do some other work. So I have y minus d squared is equal to x minus a squared plus y minus b squared. And so what I know is that I'm going to want to isolate my y, which means that I'm going to need to actually FOIL this out and FOIL this out. Because there's no y in here, I'm going to leave this. And then conveniently we can notice that my x minus a squared looks a heck of a lot like my x minus h squared. So I'm probably just going to leave that throughout the entire thing. But in order to isolate my y, I need to go ahead and square this and this to get rid of them, or to get rid of the parentheses. So if I square this according to my rules, I know that that's going to be a y squared minus 2 dy plus d squared. I'm going to leave this x minus a, and I'm going to square this over here. So I'm going to have a y squared minus 2by plus b squared. Perfect. And so now my next step is to move all my y's to my left-hand side. So what I'm going to do is I'm going to subtract this y squared, which conveniently just cancels them out. And then I'm going to add this 2by to move that over here. So add 2by. And then because y is the only thing on this side of the equation, at the same time what I'm going to do is going to move anything that doesn't have a y away. So I'm going to go ahead and subtract the d squared, which is going to move that away from this side. So now let's see what I have left. On this side I have a, let's see, a 2by minus 2dy, so far so good, equals, I have an x minus a squared, and then I have a b squared minus d squared. And so I know I need to factor out the y. I also notice they have a common factor of 2, so I'm going to split this up into two different things. I'm going to factor out my y, which means I'm going to have a y. I'm also going to factor out my 2 separately. So I have a y, 2, and I have a b minus d is equal to x minus a squared b minus d. So what I notice here is that this is a difference of squares, which means that I can split that up into a b minus d times b plus d, and that factors out, which allows me to do this. Now in order to get rid of everything attached to the y, I'm going to go ahead and I'm going to divide this by a 2, b minus d, and it's going to cancel all of this out. That means I need to divide both of these by a 2, b minus d, and a 2, b minus d. And conveniently what that does is what we noticed is that my b minus d's are also going to cancel out over there. And what we're left with is we're left with the formula in vertex form. So I only have my y over here. I have my x minus h squared is my x minus a. I'm going to shift this out to the side. So I'm going to say that's a 1 over 2 b minus d times x minus a squared. So that's the same thing. All I did was I moved that bottom part of the fraction over so that I can recognize that that's going to be my a. And then over here I have a b plus d all over 2. And what this has allowed me to do is it has allowed me to say, hey, I can compare these two functions. To get my A, I can calculate 1 over 2 times B minus D. To get my H, that's just the value for A. And to get my K is going to be this thing over here. And so I have a formula of a quadratic in vertex form using only the focus and the directrix. So let's go ahead and see how quickly this will work. As opposed to having to do this process every single time, we've created ourselves a little cheat sheet on how we can just knock this thing out. So let's take a look. What I'm going to do is I'm going to take my focus, my directrix, that's my A and my B, and that's my D. I'm going to plug it into my formula of 1 over 2 times, let's see, my B is 1, minus my D of -1, so minus a -1. And then it's going to be, okay, x minus my A, which is 0, squared, plus, let's see, I have B, which is 1, plus D, so plus a -1, all divided by 2. Kind of squishing that in there, but that'll work. So let's go ahead and simplify this. I notice that minus a negative is going to turn into plus a positive. So that's going to be 1 plus 1, which is 2. 2 times 2 is 4. So I have y equals 1/4. X minus 0 is just going to be x. 1 minus a -1 is going to be 0. 0 divided by 2 is going to be 0, of which we don't actually need to write, so I'm just not going to write it. My equation then, therefore, is this. And if I wanted to graph that, it'd be super easy. Let's just go ahead and put our focus of 0, 1. Let's put our directrix of y equals -1. Let's find 2 points along this line where I can graph this thing. I know that via this, my vertex is at 0, 0. I could have also visually looked at that, but I've now mathematically proven that it's going to be at 0, 0. Again, because the distances are the same. I also have a point right out here where the distances are 2 and 2. So I'm going to put a point right there. And I'm just going to curve up through that. Boom. And there we go. So we see how this took a ton of time off having to do this every single time. We're able to, now that we've derived a formula, plug it in and solve it in one step. So let's do that one more time to make sure we got it. So what I need to do is I need to use our handy dandy formula, and I'm going to plug in my information. So I have 1 over 2 times, let's see, this is going to be a B minus a D. So my B is -2, my D is -4. I'm going to multiply that times x minus my A squared, and my A this time is 0 again. And to it, I'm going to add a B plus D all over 2. My B is going to be a -2. My D is going to be a -4. And so let's simplify this. I have minus a negative, which means that's plus a positive. -2 plus 4 is going to be +2. Times 2 is 4, so y equals 1/4. X minus 0, that goes away, so it's just x squared. See, -2 plus a -4, so that's -2 minus 4, that's -6. -6 divided by 2 is going to be -3. And so looking at this, I'm going to expect my vertex to be at 0, -3. And let's see if, in fact, if I graph these two, if that's going to be directly between them. So my focus is at 0, -2, and my directrix is going to be at -4, which, lo and behold, yes, it is directly between those points. And so it's directly between. I noticed that over here and over here, I also have a point that's exactly 2 units away from both my focus and my directrix. So I'm going to curve up through those points. And boom, there we go. So we see the process works really quickly once we've derived a formula for us, but I think it's very important that not just here's a formula, memorize it, but that we recognize where that came from. It's literally just two distances set equal to each other, and if we wanted to, we could work all of that each time. But again, I think it's important that we know how to do it just on our own. So this time the focus is going to be moved over, which means also I'm expecting my vertex to be moved over. As with this one, I'm expecting the vertex to be moved over along with the focus. So go ahead, pause the video, try these two problems, and when you're done, resume the video and see how well you did. And I might be able to answer any questions as we go through. Okay, so let's take a look at what we can do. So with this, if I were to plot this, I would plot my focus at 3, 2, and I would put my directrix at 0, which means I'm expecting to get an h and a k that's equivalent to a 3 and a 1. So I could kind of cheat and go ahead and plug in a 3 and a 1 for that equation and only have to figure out what the a is. But for the first one, I'm going to go ahead and I'm going to work it the long way. So what I'm going to do is I'm going to say, okay, y equals 1 over 2 times b minus d, x minus a, plus b plus d all over 2. So I have a b minus d, a, and I have a b plus d all over 2. So remember, we are expecting to get a 3, 1, so I'm expecting to get a 3 right here, and I'm expecting to get a 1 right here. So again, I don't actually need to do these parts. All I'm really focused on is the a. So y is equal to 1 over 2 minus 0 is 0, or 2. 2 times 2 is 4. I have an x minus 3 squared, and then 2 plus 0 is 2. Divided by 2 is 1, exactly like what we expected it to be. So I have that. Again, I have this cheaty point that I can use that's exactly 2 and 2 away that allows me to kind of curve up through those points. Perfect. So knowing that we have kind of a cheaty method right here, and all we really need to do is find a, what I'm going to do now is I'm going to go ahead and not fill out the entire formula. I'm just going to fill out the part for a. So I know that a is equal to 1 over 2 times b minus d. That's really the only part that I need to calculate out of that. Outside of that, I can just kind of visually look and say, there's my vertex. So if my a is equal to 1 over 2 times 5.5 minus 4.5, let's see, 5.5 minus 4.5, that's 1 times 2, that's going to be 1/2. So let's see if I can't use that information to skip having to calculate all of this. So I have a focus at, I'm going to have to scale this one back. So I'm going to do this by 2's, I'm going to do this by 2's. So at 2, 4, 5, 2, 4, 5.5, and so 2, 4.5. Awesome. So I know I have those 2 points. And then to find my vertex, I'm just going to find what is exactly between 4.5 and 5.5. That's right, 5. It's actually a little lower. So I'm just going to make my point a little bigger to kind of hide that. So if that's at 5, the focus has been moved over 5. That's up 5, so my vertex is at 5, 5. So I know it's going to be 1/2 x is 5, because I know that it's right there, squared, plus 5, because my vertex has been moved 5 up. I didn't even need to plug it into the formula. I can just deduce that because I know where my vertex is. And so what I'm going to do is I'm going to say, okay, that's a distance of 1, which would mean that I need a distance of 1. Actually, it's a little, yeah, no, it's good. So I'm going to have a point here and a point here, and I'm going to curve up through them. Boom, and there we go. So today we're going to be going over polynomial identities. These are things that we've already learned how to do by hand, but we're going to learn a few quick and hard set rules that we can write down so that we can do problems like these in one step without having to show any of our work. So the whole reason of studying identities is, again, we know how to do the long form of these, but if we plug in some generic numbers, so numbers that I can replace anything with. So like, I'm going to take my 6r and I'm going to assume it's an a, but what happens if it's not a 6r? Would it still work? Well, let's go ahead and figure out what we would do. So if I have an equation like a plus b squared, that's telling me that I have a plus b times a plus b. I am going to distribute my a to both terms. So I'm going to get a times a, which is a squared, a times b, which is ab. And then I'm going to go ahead and distribute my b to both terms. I have b times a, and then I have b squared. Well, I notice the fact that these two middle terms, it's ab, and basically this is ab, it's just backwards. So I can combine those, there's two of them. So I have a squared plus 2ab plus b squared. And this is our first polynomial identity. It's a plus b squared. So what we've got going on is the fact that if we ever see a perfect square trinomial like this, I know I'm just going to square the first term. I'm going to square the last term. And then I'm just going to multiply the two numbers together and double it. So if we have a sample problem like this, without having to do any work, without having to show our steps, we can just say, hey, I'm going to square this first term. 6 squared is 36. R squared is r squared. I'm going to square the last term, so I'm going to get a w squared. And then in the middle, I'm going to multiply the two things together. 6rw times 2 is 12rw. And boom, we knock it out with no steps. So another polynomial identity is the fact that let's reverse that. So with a perfect square trinomial, what we notice is that we have a perfect square in our first term, perfect square in our last term, and we have double the product, basically this thing right here. But this is typically how we're going to see it. We're going to look at it and we're going to say, hey, I recognize that I have a squared number and a squared variable, and then I have a squared number. And I'm going to look at the number in the middle, I'm going to say, hey, if I take the square root of each end, so that 25, if I take the square root of it, that 49, if I take the square root of it, multiply them together and double it, is that what I see? So the square root of 25 is 5, square root of 49 is 7. So 5 times 7 is 35, double it is 70. Yes, this is going to check off for what we're about to do here. So how do we factor this without having to list a set of factors of whatever 29 times 4 or 25 times 49 is? Well, let's factor this one so we can create a rule for every single one of these. So if I have some number, we know typically the way that we factor is I'm going to take the constant and multiply it times the constant, or I guess the coefficient, multiply it times the constant. So I'm going to say AC, or a squared times c squared is going to be a squared c squared. And I'm going to try and find a set of factors that, because this is positive, that make a sum of 2ac. Okay? So what two numbers? Well, what I could do is I could say a times ac squared. I could say a squared times c squared. I could say a squared c times c. There's a bunch of different possible factors that I could have, including, if these were bigger numbers, any possible sets of factors that they come up with. But the one that we're after right here is going to be AC times AC. Because AC times AC is a squared c squared. And if I add these two together, I get 2ac. So I know how I'm going to split that middle term up. So I'm going to say a squared plus x squared plus c squared. I'm going to split that middle term into basically ac, ac. Okay. And then I'm going to create a factoring by grouping. I am not sure why I put a plus sign right there. That is going to be a times sign. A squared, x squared. I'm not going to suddenly introduce an addition problem. I'm going to take the GCF out of each one of these. The GCF over here is going to be a, oh, hold on, again. My AC, each of these ACs has an x, because it's ACX plus ACX equals 2ACX. So I'm going to pull out an A because they both have an A, and an X because they both have an X. Over here, I'm going to pull out a C, which means if I pull out an AX and a C, what's left over? If I take away an A, I have an A. Take away an X, I have an X. Take away an A, I have a C, and I don't have an X. So X plus C. If I take away my C, I have an AX. Take away one of the C's, I have a C. And perfect. What I notice is that yet again, I'm going to do this one in red. I'm going to have an AX plus C that I can pull out of that. So I have AX plus C times AX plus C, or AX plus C squared. And so this is my second polynomial identity, which is just the flip side of this. We have our ax plus c, our a plus b squared. In this, we're just showing there may be a variable attached. So let's take a look at this. Okay, if I know that I can take the starting form and convert it all the way to the end, I'm going to say, okay, I need to find the square root of that number. So the square root of 25 is going to be 5. I'm also going to take the square root of that variable, x. Square root of 25x squared is 5x. And then I'm going to need to take the square root of that number on the end. 49, that's going to be a 7. And because this was a positive, I'm going to include it as a positive. Boop, boop, squared. There we go. No steps necessary, because we've proven that it works for any combination that follows this pattern. So let's do another type of factoring and foiling combinations. If I have a difference of squares factoring, I'm going to do the same thing that we just did right here. I want to come up with a rule. If I ever see a set of factors like this, I notice that everything's a perfect square and everything's a perfect square. Can I come up with a hard and fast rule to where I don't need to show a bunch of steps? Because as of right now, I'm going to have to multiply 49 times 64, like we did up here. And that's going to be a really big number to make a list of possible factors. So let's see if we can't speed that up a bit. Okay, so what we need to do is I need to multiply the first one times the last one. I notice that I don't have a middle term. So my middle term must be a 0. So 0ab. It doesn't exist. But I'm going to take a squared and b squared. And I have an a squared, b squared. Pretty simple. And this time, because it's negative, I need a difference. I need them to be separated, or taken the difference of that 0 term, that missing term. And so again, I could go through the entire list, but I bet you if I do AB and AB, AB minus AB is going to be 0. So that's exactly what we're going to do. We're going to take our a squared, and I'm going to add an AB, and I'm going to subtract an AB. Because AB minus AB is 0, so I didn't actually change that. I just introduced this arbitrary thing. I'm going to factor out the GCF of both sides. See, I have an A over here. I have a leading coefficient of negative, so negative. B in both of those. So I'm going to pull out an A and a negative B. That's going to leave me with an A plus B,
Over here it's going to leave me with an a, and it changes the sign, plus b. Hey, so I can divide out the a plus b. So I have an a plus b that I pulled out, and I'm left with an a minus b right there. So there's my third polynomial identity. If I notice that I have perfect squares on both sides and there's a different sign between them, I can just spit out this quick and hard rule and say, okay, I'm going to take the square root of 49x squared, which means I square root both of these, which is going to be a 7x. And I'm going to square root the last thing. So 64 and y squared, well, that's going to be an 8y. And I'm going to add it, and then I'm going to write it again with a subtraction sign. Boom, 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 boom. No steps necessary. There you go. The last one. The last one right here. Again, when I see that I have two 10s and two 2i's with different signs between them, I wanted to see if I couldn't come up with a hard and fast rule, which we'll see that, hey, we're going to end up reversing this. So let's take a look at how we work this. I'm gonna multiply my a by distribution, so I get an a squared minus ab. Then I'm going to distribute my b, so I have ba, or I'm just going to rewrite it as ab, and then minus b squared. I notice that these middle two terms, they're going to cancel out. So I'm left with a squared minus b squared. So again, I showed that I can FOIL this. Basically, I can FOIL this and end up back with this. And this is my last polynomial identity. So if I ever see something that's plus and minus, I'm going to say, okay, I'm going to square the first thing, 100. And I'm going to subtract, square the second thing. So 2 squared is 4, I squared is I squared. Except for this one, we're not done. Because with this one, remember what I squared is. If I is the square root of -1, then I squared is a square root of -1 squared, or just -1. So that's actually 100 minus 4 times -1, which is plus 4. So it's actually 104. And this is a big thing that we're going to be seeing coming up, is conjugates with lateral numbers, or conjugates with any sort of complex numbers. And there we go. Some official polynomial identities. So today we're going to be dividing polynomials. Then we're going to see what it looks like when I take a long expression like this and divide it by an expression that's a little shorter down there at the bottom. Now, the process through this is extremely similar, and it's basically the same thing as long division. But I think it's important to point out why we're doing this. One of the big things why we do polynomial division, let's say I have a graph, and I have a graph just like this. Well, we know from the fundamental theorem of algebra that my graph is going to have bends in it. In fact, with 3 roots, that means it's going to have 2 bends. So it's going to go 1 bend, 2 bend, and it's going to do that. And the reason why it's a power of 3 is that we know that we have 1, 2, 3 spots where it intercepts the x-axis. And what we're going to try and do by finding these is we're hoping to find these 3 roots by doing this division process. Because let's say I have something like x equals, let's say that's 3, let's make that an x equals 6, and that's an x equals 10. Well, I know that from those 3 values, if I solve for 0 and move that 3 over, that's going to be an x minus 3. That one's going to be move the 6 over, x minus 6, and move the 10 over, that's going to be an x minus 10. Now, realistically, this graph is not going to be represented by this. There's going to be scale factors in here that have moved the graph over and then have scaled it the way it is. But again, we're assuming a kind of more of a standardized graph. This is just an alliteration of what's going on. And if I were to FOIL these, let's see, that's x times x, that'd give me an x squared minus 3 minus 6 is minus 9x plus 18. And then if I took that x minus 10 and foiled that in there, let's see, that would give me an x cubed minus 10x squared minus 9x squared is minus 19x squared plus 90x plus 18x is going to be plus 108x. And then that's going to be a minus 180. What I'm hoping to do by doing this process is that I multiply this out. I'm hoping that if I divide by something like, take this and divide by an x minus 10, what I'll end up with is removing this from the equation. Actually, let me do this in a different color. If I want to divide this by an x minus 10, I'm hoping to remove it from this equation and end up with something that I can easily factor to find the other two roots. And if I divide this and I have no remainder, what that means is the x minus 10 is that I have found, let's do this in purple, no remainder. That means I found that root. And so again, that's kind of the idea of what we're doing with dividing polynomials, is we're hoping to find those 3 points. So let's go and get started. The process is not too difficult. It's just like long division. With long division, if I said, hey, let's take, for example, if I said let's take 4 over 2, I would say, how many times does 2 go into 4? Actually, let's do 412. What I would do is I'd move that number to the outside. So I'm going to do exactly that. I'm going to say x plus 7. I'm going to take the top number and slide it over here. So I'm going to take the x cubed plus 8x squared plus 10x plus 21. I'm going to divide it in there. And now the same thing, normally we ask the question, 2 fits into 4 how many times? I'm going to ask a slightly different question. 2 times what gives me 4? And most of you would answer, well, 2 times 2. And we put the 2 up there, and then we multiply 2 times 2. It's going to give me 4, and we'd subtract. So I'm going to do the same thing. I'm going to look at, I'm only going to look at the first term in each one. I'm not going to care about the 412. I'm only going to care about the 4. So x times what gives me x cubed? Same thing like that. And that's going to be an x squared. And then we multiply that times there, and we got the number down there. So I'm going to do the same thing with this. I'm going to say, okay, so x squared times x is going to give me an x cubed. But I also need to multiply times the 7. So plus 7x squared. And so what I'm going to do is I'm going to go ahead and let's do this in, let's do it in purple. When we had this, I didn't say 4 plus 4. I changed the sign. I said, okay, let's take it away to get a 0 so I could move on. So what I'm going to do right here is I'm going to change the sign. I'm going to change this to a minus. And it's going to cancel those out. So I have 8x minus 7x is going to give me an x squared. Drag down my 10x, just like I would drag down my 1 and drag down my 2. I'm going to keep doing that. I'm going to repeat the process. X times what gives me an x squared? Again, I'm only looking at the first term. That's going to give me an x times x is going to give me an x squared. So then I go through the process and I multiply and I say, okay, x times x is going to give me an x squared. X times 7 is going to give me a 7x. And then I'm going to go through and I'm going to change the signs. So that's a minus, and this is now a minus. X squared minus x squared, it cancels out. 10x minus 7x is going to give me a 3x, and I'm going to drag down my 21. And I'm going to repeat the process one more time. I'm going to say, okay, x times what gives me 3x? 3. Okay. I multiply 3 times x, I get 3x. 3 times 7, it gives me 21. And then the important part about right here is that I have no remainder. When I subtract this and I subtract this, my 3x and my 21 cancel out. I have 0 as a remainder. which means that I found one of the roots. So if I were to graph this like I did over here, that would mean that x plus 7 or negative 7 on the x-axis is going to be a root. We found one of them. So awesome. That works. A zero remainder means that that is the exact answer and that that is a root of this polynomial. So now that you've kind of seen how it's done, try the next one. Go ahead, pause the video, give that one a shot. It's got to the power of 4, but it's solved exactly the same way. And see if you can get to, this one should also have a zero remainder. So see if as you work it out, you get to the same thing of a zero left over. Resume the video when you're done and see how you did. Okay, so let's see how we did. So what I'm gonna do is I'm gonna take that bottom and the n plus 2, and I'm gonna put it off to the side. And I'm gonna take my 5n to the 4th plus 14n cubed plus 12n squared plus 14n plus 12, and I'm gonna put it beneath my division sign there. And then I'm just gonna only focus on the first of each term each time. I'm gonna say, well, I need to multiply n times 5 to get that 5, and I need 3 more n's. And I'm gonna multiply. 5n3 gives me 5n4. 5n3 times 2 is gonna give me 10n3. And then I'm going to subtract it. Cancel out, perfect. That's gonna give me a 4n cubed, and I'm gonna drag down my 12n. And I'm gonna repeat the process. So literally, that one step is all we're doing. I'm just repeating it 1, 2, 3, probably 4 times. So I'm gonna need to multiply by 4, and I need 2 additional n's, and I'm gonna go ahead and I'm gonna distribute that. 4n squared times n is 4n cubed. 4n squared times 2 is 8n squared. So let's go ahead and subtract. It's going to turn that into a minus. It's going to cancel that one out. 12 minus 8 is going to give me 4. Okay. Again, I'm only looking at the first term. I'm going to say, okay, n, it looks like times 4, and I need 1 more n. I'm going to multiply that. 4n times n is going to be 4n squared. 4n times 2 is going to be 8n. So I'm going to go ahead and I subtract it, cancel out, and I'm left with 14 minus 8 is 6n plus 12. And now this is where I really hope that my two numbers right here are going to be equal. Because if so, that means I found one of these roots. If not, that means I'm somewhere else. I'd rather this be for a purpose. So n times 6 would give me a 6n. So 6 times n is going to give me 6n. 6 times 2 is going to give me a 12. Perfect. So what we know is the fact that with this, both of these cancel out. I have a 0 remainder, which means that, yes, this is exactly the answer. That means that n plus 2 is a root of that. In fact, if I were to draw a sketch, that would mean that n is negative 2. I don't exactly know where the other zeros are going to be, but I know it has 4 roots, so that's going to be 1, 2, 3, 4. Actually, this is a true sketch because that's supposed to be flipped up, but regardless, it's just an idea of what's going on. What we know is the fact that I found that n equals negative 2 because n plus 2 is a root. We found that one. No idea where the other 3 are. They're somewhere hidden within this, but I know I found one of them because there was no remainder. Perfect. And so one of the logical questions you might ask is, well, what happens if it doesn't zero out? What does that mean? It just means that we missed the 0, but what does it look like? Okay, so let's take a look at what that would look like. Again, I'm going to take my x minus 4 and move it out to the side, and I'm going to write my, I believe this is the dividend.
I'm not actually up to date on the terminology for what is the divisor, what is the dividend. I think that is, actually I think that might be the divisor and this is the dividend. Or vice versa, it doesn't matter. I'm going to take the top, we'll call it the numerator, and get around that problem and put it up there. Again, the beginning is going to look the same. We're still going to try and make this work. I'm going to say, okay, x times negative 8x squared is going to give me a negative 8x cubed plus 32x squared. I'm going to subtract, which means that I'm going to change this to a plus and that to a minus. Cancel out. 40 minus 32 is going to give me an 8. Drag down my 37. Gotta do it again. And ask, okay, I need x times 8, and I need another x to make that work. So it's going to be 8x squared, if you believe that that's a 2. 8 times negative 4 is negative 32x. We're going to subtract it, which means that this is now a plus. Cancel that out. I have negative 5x plus 30. And now this is the important step, because when we try it right here, and we say, okay, what would make x fit into 5x? I get a negative 5. And the problem is that when I run that through and I say, okay, that's a negative 5x plus 20, I notice those aren't going to cancel out. So as I make that a plus and make that a minus, cancel out, and I'm left with a remainder of 10. Which basically just means that I missed it. So unfortunately, I'm going to have to take that 10 and say plus 10 over x minus 4. And now this is going to be my answer. And while I did the long division correct, this isn't a very useful answer, because what it means is the fact that I missed my 0. So let's see, let's draw this a little more accurate. I have third power, which means it has 3 roots, and negative, which means it's going down. So what I know is the fact that my graph has, so up, okay? So it's going to be 3 roots, which means it has 2 bends. It's going down. I was hoping to find these 3 points. I thought one of them was going to be at 4. But I had a remainder of 10, which means I kind of missed. So somewhere at x equals 4, I hit a remainder right here, which means that I missed my root. And we'll learn later on that this actually isn't a bad thing, because when we learn how to use synthetic division, by the fact that we missed the root, we're going to look at how we missed it to see if we can't find where it is. So that's okay. This is okay. It just means that, albeit it wasn't as useful as it would have been up front. So what I want you to do is I want you to pause the video, try the next one, and see if you can get it to be a remainder of 0. Unfortunately, this one also is not, but see if you can figure out what the remainder is going to be. Okay, let's take a look at what's going on. So I'm going to take my n plus 6, and I'm going to try and divide it into n cubed plus 15n squared plus 47n minus 38. Awesome. Pay attention to my first numbers, and I'm going to say, n times n squared is going to give me that thing. N cubed, n squared times 6 is 6n squared. I'm going to go ahead and subtract it, which means I'm going to change that to subtraction, cancel out. 15 minus 6 is going to give me a 9n squared. Drag down my 47. And again, look at my first term, right there and right there. I'm going to say n times, well, first off, times 9, and I need an additional n.
So let's see what that would do. So 9n times n is going to give me 9n squared. 9n times 6 is going to be 54n. I'm going to go ahead and I'm going to subtract. Cancel those out. 47 minus 54 is going to give me a negative 7n. Drag down my minus 38. I'm going to look at my first terms. And so I hope that they're going to cancel out so that I have a 0 remainder and I don't end up with that. But as we see right here, when I pick my negative 7 and I distribute it to my, again, divisor, I believe, negative 7 times n is negative 7n. That's going to cancel out, but I get a negative 42. So unfortunately, when I change these to positives so I can get rid of them, I don't get rid of everything. I have a remainder of 4. Which means, again, if I were to graph this over here, this is a cube root, which means it's going to be like this. It's going to have 2 bends. This one's going to end up going up. So, should have drawn that farther over. In fact, I'm just going to move this axis over here. We're going to ignore this axis. Doesn't exist. So I'm going to say 1 bend, 2 bend. And so what I was hoping to find is I was hoping to find these 3 points wherever they may be. Now this might actually be shifted over here, it might be shifted over there. Not exactly sure. I was hoping to find one of these, but I ended up noticing that at negative 6, so x equals negative 6, or in this case my n, so n is equal to negative 6, I got a remainder of 4, which means that I had something left over ending at 0. So that just means that I missed my root. And so I'm going to have to pick a number a little farther over and maybe try x plus 7 and see if that will kind of scooch it over. But again, we'll learn more about this in a future lesson. That's how we divide polynomials.